When a child asks for the biggest number, we usually play along. 1,000,000, 1,000,000,000,000. But you can always add 1. There is no biggest number. Numbers go on forever. This endlessness is what mathematicians call infinity, the process of never ending without stopping. This process exists in the smallest of spaces. This number line is bounded strictly between the digits 0 and 1. Pick any 2 points and you will find an endless supply of numbers hiding in the gaps. 1/2 is in there, 1/10, but also 0.01, 0.001. No matter how close 2 points get on this line, you can always squeeze another decimal between them. This means the number line has no final gaps. The endlessness tightly packed between 2 adjacent points gives us our baseline. Infinity is the property of going on forever without stopping, no matter how far you zoom in. In 1924, mathematician David Hilbert proposed a thought experiment to test how this property behaves. He imagined a hotel with an infinite number of rooms. Every single room is occupied. A guest is in every room. The hotel is completely full. Then a new guest arrives. In a normal hotel, you turn them away. But here, you ask every current guest to move 1 room forward. The guest in room 1 moves to room 2. 2 moves to 3, and so on, forever. Room 1 is now empty, and the new guest checks in. Now imagine an infinitely large bus of new guests pulls up. To fit them, you ask every current guest to move to double their room number. The guest in 1 goes to 2, 2 goes to 4, 3 goes to 6. Suddenly, all the odd-numbered rooms are empty. Room 1, 3, 5, 7, an endless string of vacancies ready to absorb an entire infinite bus. This diagram shows what is happening underneath the surface. Mathematicians measure the size of sets using cardinality. 2 sets have the exact same size if you can match their items 1 to 1. By perfectly pairing every natural number with an even number, every item gets a match, no leftovers. Every even number matches a natural number. This means the set of even numbers is exactly the same size as the set of all numbers combined. Half of an infinite set is identically as large as the whole. Our standard arithmetic simply does not apply here. Whole numbers behave strangely, but what about fractions? Between any 2 whole numbers, there are infinitely many fractions. Visualizing this massive sea of numbers suggests it must be a larger infinity. This is a grid showing all positive fractions organized by their numerators and denominators. Look at the scale of this layout. Pause the video for a second. Try to find a path that lets you count every single fraction one by one. If you just go straight across row 1, you will count endlessly and never reach row 2. How do you map them all? The solution is a winding diagonal path. By weaving back and forth through the grid, 1 over 1, 1 over 2, 2 over 1, and so on, this path visits every single fraction. As it touches each one, we can assign it a sequential counting number. Because this perfect pairing exists, the set of all fractions is exactly the same size as the natural numbers. They are what we call countably infinite. They fall entirely within our baseline infinity. In 1891, the mathematician Cantor pushed this rule to its limit. He asked if the same trick works for the real numbers, all those endless decimals tightly packed between 0 and 1. Can they be listed and matched just like the fractions? To find out, Cantor used a proof by contradiction. Look at this numbered vertical list of long decimals. Let's assume this list is 100% complete. Every possible real number between 0 and 1 is captured right here. Cantor targets the diagonal. He looks at the first digit of the first number, the second digit of the second number, and so on. He pulls those exact digits down to form a decimal, and then he changes every single one of them. A 5 becomes a 6, a 3 becomes a 4. He builds a brand new sequence. Now look closely at this new number. Is it anywhere on our complete list? It cannot be the first number, because the first digit differs. It cannot be the second, because the second digit differs. It is guaranteed to be completely unique from the nth number on the list at the nth decimal place. We built a number perfectly designed to dodge every single slot. The assumption is broken. A complete list of decimals is impossible. This unlistable scale is called the cardinality of the continuum. As this comparison shows, Aleph null absorbs whole numbers and fractions. But the dense line of real numbers, labeled C, is a strictly larger infinity. They cannot be paired. They cannot be contained in any infinite hotel. This reveals infinity as a multi-tiered landscape where some portions are provably larger than others. This hierarchy creates a foundation for a new question. If infinity can be this vast, can infinitely many numbers ever sum to something finite?